Today, we are going to discuss a sample problem based on our topic, vapor compression refrigeration system. I will be giving one problem. In this problem, I am going to illustrate how you are going to find different quantities, and then also by using tabulation, how to make calculation much easier. Here is the problem. A simple vapor compression cycle develops 13 tons of refrigeration using ammonia as refrigerant and operating at a condensing temperature of 24 degrees Celsius and evaporating temperature of negative 18 degrees Celsius, and assuming that the compression are isentropic and that the gas leaving the condenser is saturated. First, draw the pH diagram and then determine the refrigerating effect, the mass flow rate of refrigerant, the power requirement of the compressor, the volume flow rate of refrigerant at compressor inlet conditions, coefficient of performance, power per ton, rate of heat rejection to the environment, the fraction of vapor in the mixture at the entrance to the evaporator, and also determine the coefficient of performance of the cycle if the expansion valve is replaced by an isentropic turbine. The first question is for us to draw the pH diagram. So draw the pH diagram. So the pH diagram looks like this. So we have the pressure on the y-axis and then the enthalpy on the x-axis. So for a vapor compression cycle, this is how the cycle would look like. We have 0.1, 0.2, 0.3, and 0.4. And we are given in the problem that the condensing temperature is 24 degrees Celsius. So we have 24 degrees Celsius in the condenser side. And then we have negative 18 degrees Celsius in the Okay, so we have negative 18 degrees Celsius in the evaporator side, and then in the condenser side we have 24. That's why we have negative 18 degrees Celsius. So this is how the pH diagram looks like. As you can see, we only have two pressures here. We have pressures at 24 degrees Celsius and pressures at negative 18 degrees Celsius. The second one is for us to solve the different quantities that is required in the problem. For this problem, I decided to give many sub-questions for us to better understand how to get those quantities, just in case they will arise in some problems. So before you can do that, first you have to tabulate the state properties. So by tabulation, this is how the state properties based on the given. At state 1, this is a saturated vapor. We have point, state, pressure, temperature, entropy, quality, and then enthalpy. These are the properties that we are going to get using our software or using refrigerant table. So it's good to tabulate them so that it will be easier for us to track the properties, and thus easier for us also to get the unknown properties. We have this cycle, we have 4 points. We have point 1, 2, 3, and 4. That's why we have 4 points here in the table. And then the state are also known. At point 1, the state is saturated vapor. Point 2, that is a superheated vapor. So at point 2 here, this is a superheated region. And then point 3, this is a saturated liquid. It's at this side. So we have saturated liquid. And then point 4 is in the mixture region. That's why it is a mixture. And also based on the given, we are given with the temperature at point 1, since this is the temperature in the evaporator side. That's negative 18 degrees Celsius. So just add 273.15. That's why we have 255.15 here. This is the temperature at point 1. Take note that the temperature at this point here is just the same because this is a saturated region. And then at point 2, the temperature is unknown because this 24 degrees Celsius is only the temperature in the saturated region. This is the temperature of the saturated region of the condenser. It's 24 degrees Celsius, but beyond that, it's not 24 degrees Celsius. That's why this one is still unknown. Under at point 3, we have this one is saturated region. That's why it's 24 degrees Celsius plus 273.15. That's why we have 297.15 here. At point 4, it is the same temperature as point 1. That's why we have 255.15 Kelvin. So far, these are the known. So from thermodynamics, we learned that if we know two property, then we can identify the other properties, the unknown properties. We have here the state at point 1 is saturated vapor, and then the temperature is 255.15 Kelvin. So using the software, the refrigerant software, here we are going to use the property of ammonia. So go to the property of ammonia as your refrigerant, and we are going to locate the unknown properties. So using that, using this temperature of 255.15, and then knowing that this is a saturated vapor, then we can get the pressure at point 1, and that is based on the software that is 207.56 kilopascal. So the temperature here at point 1 is PSAT. So the PSAT at 255.15 Kelvin. That's why we have 207.56. Also, for the entropy, it is the entropy sat at or SG at point 1. That's why we have 6.35 kilojoules per kilogram Kelvin. The quality, because this is a saturated vapor, then obviously this is 100% vapor. And then for the enthalpy at point 1, that is the saturated vapor enthalpy at 255.15 at point 1. That is Hg at point 1, or Hg at negative 18 degrees Celsius or 255.15. That's why we have 1583.5 kilojoules per kilogram. So we already have all the properties in point 1. Now we are going to get the property at point 2. So far, we only know that this is a superheated vapor. But one thing is for sure, we know that process 1 to 2 is an isentropic process. So therefore, S1 is equals to S2. That is the reason why our entropy at point 2 is 6.35 kilojoules per kilogram Kelvin. And since we already know that this is superheated vapor and the entropy is 6.35, all we have to know is another property for us to know the other properties. Also know that at this line here, this is a constant pressure line, right? This is the pressure at the condenser side, and then we have pressure at the evaporator side. This tells us that the pressure in point 3 is equal to the pressure in point 2. This is why we can, if we know the pressure at point 3, then we can get the pressure at point 2. And basically that is just 972.68. That is PSAT at 24 degrees Celsius. So the saturation pressure at 24 degrees Celsius for ammonia is 972.68. That's why we have 972.68. So now we know the pressure at point 2. Again, the pressure at point 2, since this is a constant pressure line here, then this is the same, 972.68. So now we know that if we know two properties as well as the state, then we can get its other properties. Go to the, the software and then just input 972.68 for pressure and then 6.35 for entropy, and we can get temperature as 364.46 Kelvin, and then enthalpy as 1806. So as you can see now, the temperature is different from point 1. It does increase from 255 to 364.46. It is also the point that has the highest temperature among the states. So obviously this is the highest temperature because this is a superheated vapor. Also make sure to check those aspects for you not to verify the results. And the enthalpy as well has increased because of the increase also of temperature. So we have 1806 kilojoules per kilogram. So at point 2, we learned that this is a constant pressure line here. This is the reason why the pressure at point 2 is equal to the pressure at point 3, and that is Psat at 24 degrees Celsius. That's why at point 3, which is a saturated liquid, we can get the pressure as 972.68, and they are just equal to point 2. And since we already know that this is saturated liquid, even without knowing the pressure, we can get quality as well as the enthalpy. Since this is saturated liquid, there is no vapor, so this is 0% quality. And then the enthalpy is HF at 24 degrees Celsius. So HF at 24 degrees Celsius, or HF at 297.15 Kelvin for ammonia, so we have 456 kilojoules per kilogram. So next we have point 4. So we know that point 4 is an expansion process. So I say a throttling process. So obviously, H3 is equals to H4. This is the reason why the enthalpy at point 4 is 456. That is just equals to H3. And then for the pressure, that is the pressure at negative 18 degrees Celsius. Same also with the pressure at point 1, so that is 207.56. Finally, we were able to get all the enthalpies that we will need later on for us to solve the different quantities. So we are just going to complete the table first by solving the quality at point 4. Since this is a mixture, meaning this has a quality. Quality is the amount of vapor that is present in that fluid. So for us to determine the amount of vapor, then we will just use the formula H4 minus HF over Hg minus HF. This comes now from our formula that H4 is equals to HF plus X4 HFG4. If you're going to rearrange that, then X4 will be H4 minus HF over HF minus Hg, or Hg minus HF. So from this, we can get the quality at point 4. Since we know that H4 is 456, then just plug in. HF is the enthalpy of the liquid, saturated liquid now at negative 18 degrees Celsius. That we can get that also using the software, and that is 260.76. Try to find HF at negative 18 or HF at 255.15, that is 260.76. And then Hg is equals to H1. The HF is here. We were not able to get that in the table because that's not one of the correct requirements. But the Hg is equals to H1. That's why we have 1583.5 here. And then HF is again, that is the HF at negative 18 degrees Celsius. That is 260.76. So from that, we can get the quality at point 4, and that is 14.8%. We have 14.8%, so you can put that now in the table to complete the table, and finally 0% for the saturated liquid quality. So we were able to complete the table, and this will be the properties that we will use to compute the other quantities. So we are going to summarize all the enthalpy. So these are the enthalpy at point 1, point 2, point 3, and point 4. Make sure that point 2 has the highest enthalpy because this is the point with the highest temperature. Followed by point 1, H3 and 4, they have the same temperature. That's why they have the same. And this is an expansion process. That's why they have the same enthalpy. So we are going to compute first for the refrigerating effect. So we all know that refrigerating effect is difference between the enthalpy at point 1 and point 4, which is the inlet and the exit point for the evaporator. So this is the evaporator side here. Then we have the condenser. Then we have here the compressor. Then we have here the expansion valve. So for the refrigerating effect, it refers to the evaporator. And the formula is just Q(L) is equal to the difference between enthalpy at point 1 and point 4. So from our table, we can get H1 and H4. So that's just substitute. So our refrigerating effect is 1,127.5 kilojoules per kilogram. So when we say refrigerating effect, this means this is the effect that the refrigerant can cause, no, and produce in the evaporator. So that's 1,127.5 kilojoules per kilogram. So refrigerating effect is different from refrigerating capacity, because capacity is usually in kilowatts. Next is the mass flow rate of the refrigerant. As you can see, this is just one cycle or one loop. Therefore, by conservation of mass, the mass at point 1, 2, 3, and 4, they are just the same. So we can create an analysis now at the evaporator. We all know that there is a refrigerating effect here of 1,127.5, and then we are given with the tons of refrigeration, which is equals to 13 tons of refrigeration. The tons of refrigeration is the refrigerating capacity in tons. All we have to do is to convert that into kilowatt and then use that as our way to get the mass flow rate of the refrigerant. So from our formula, our QL is equals to the mass of the mass flow rate of the refrigerant times the small QL, or the refrigerating effect, or the tons of refrigeration is equals to the mass of the refrigerant, mass flow rate, and then the refrigerating effect. So for QL, this is the refrigerating capacity, and this is given as 13 tons. So this is the conversion factor. This is different from mass now, measurement of tons, but this is tons of refrigeration, or TOR. So 13 tons of refrigeration, you can convert that to kilowatt using the conversion factor. 1 ton is equals to 8.516 kilowatt. So multiplying, we have refrigerating capacity is 45.71 kilowatt. So by substitution, our formula for the mass flow rate of refrigerant, then solving for the mass flow rate of refrigerant, we can get the mass flow rate as 0.045 kilogram per second. So therefore, the mass of the refrigerant that is flowing in this refrigeration system is 0.045 kilogram per second. That is how you get the mass flow rate, and you can convert that also to minute by multiplying it by 60. That is 2.43 kilogram per minute. So now we answered refrigerating effect, mass flow rate. The next unknown is the power requirement of the compressor. So the compressor is between 0.1 and 0.2, and we are looking for power. That's why we have to make sure that our answer is in kilowatts. So the power in the compressor can be written as the mass flow rate of the refrigerant. So again, this is the same mass that flows all throughout, so we can use that mass here, multiplied by the range of enthalpy in the compressor. So from the table, we already have the enthalpy, and the mass flow rate is also known. That's 0.045 kilogram per second. By substitution, we can get the power requirement of the compressor as 9.01 kilowatt. Meaning this is the power that you will need from the electrical source. That is 9.01 kilowatt. So we need to make sure that the power requirement should be as much as possible lower for us to obtain a lower power input and higher coefficient of performance. Next is the volume flow rate of refrigerant at the compressor inlet. So here it is important also to calculate the volume flow rate of refrigerant at the compressor inlet, because this will help us also in designing or choosing the right compressor or the performance of the compressor. So the volume flow rate of refrigerant at the compressor inlet can simply be written as mass over density, or the volume flow rate is the mass flow rate divided by the density of the refrigerant at 0.1. So now, this came from the formula density is equals to mass over volume. We just rearranged that. That's why we have the volume flow rate is the mass flow rate divided by the density at 0.1. For the density, this is the density at the compressor inlet at 0.1. We need to get the density at 0.1, and we can get that using our table. Using our table of properties or using the software. The density is the same now. You're just going to solve as the density at the temperature, which is negative 18 degrees Celsius. On the density at negative 18 degrees Celsius, make sure that it is saturated vapor density. So this is 1.7413 kilogram per meter cube. Again, density as saturated vapor density at negative 18 degrees Celsius using the software. So that is why we have density of 1.7413 kilogram per meter cube. Since we already have the mass flow rate, all we have to do is just to substitute them, and then our volume flow rate is 1.4 meter cube per minute. So this tells us that per minute, the volume of refrigerant that is flowing in the compressor inlet is 1.4 meter cube. Next one is the coefficient of performance. So again, the coefficient of performance tells us how efficient your refrigeration system is. And that can be computed using the formula QL over work of the compressor, or the refrigerating effect or refrigerating capacity divided by the work of the compressor or the power in the compressor. So it can use now the small QL or the big QL or the small W or the big W, as long as they have the same unit. The coefficient of performance, so our QL is, we already computed that as 45.71 kilowatt, and then the work at the compressor or power requirement at the compressor is 9.01 kilowatt. That's why our COP is 5.067. What does the COP tell us? The COP of 5.07 tells us that for every 5 refrigerating effect, you will require for every 5 kilowatt of energy that you use, you will be able to produce one amount of refrigerating effect. So, or it's vice versa, no? It's like that. So it should be, the COP is telling us that refrigerating effect is 5 times the amount of energy that you use for this refrigeration system. Okay, the next one is we're looking for the power per ton. So from the name itself, all we have to do is just to divide power by the ton of refrigeration. Of the power is 9.01 kilowatt, which is the power required in the compressor, and the ton of refrigeration is 13, and that is given. So the power per ton is 0.6931 kilowatt per ton. The power per ton will tell us how much power is needed for us to produce 1 ton of refrigeration. So for us to produce 1 ton of refrigeration, we need 0.6931 kilowatt of energy. And then the next one is the rate of heat rejection to the environment. As you can, if you are going to analyze it, the part here that involves rejection to the environment is in the condenser, and that is between 0.2 and 0.3. That's why the rate of heat rejection, since this is rate, we will use kilowatt. The big Q, or QH, is equals to mass flow rate of refrigerant, and then the change of enthalpy between 0.2 and 3. Substituting, so we have 54.7 kilowatt. So the rate of heat rejection to the environment is 54.7 kilowatt. You can see this is an enormous amount of energy, because our power requirement for the compressor is 9.01 kilowatt, but this one is 54.7 kilowatt. The fraction of vapor at the entrance of the evaporator. The fraction of vapor is referring to the fraction of vapor that enters at 0.4, because this is the entrance of the evaporator. And we already computed that, and that is, we can find that in the table, the mass of the vapor, or the quality at 0.4, which is 14.18%. So as you can see, we were able to solve all of the requirements. The table, we already also created the pH diagram, refrigerating effect, mass flow rate of the refrigerant, power requirement of the compressor, volume flow rate, coefficient of performance, power per ton, rate of heat rejection to the environment, and the fraction of vapor at the entrance of the evaporator. So each of these will give us an idea how efficient or effective this refrigeration system is. And the coefficient of performance is quite good, and that is 5.07. So you can try to experiment instead of using ammonia, try solving problems and use other refrigerant and try to examine what will be the coefficient of performance if we use that kind of refrigerant. There is also a question that to determine the coefficient of performance of the cycle, if instead of using expansion valve, you replace the expansion valve to use an isentropic turbine. So from the name itself, instead of using an expansion process, wherein a throttling process wherein enthalpy is constant, here we replace it with isentropic turbine that is isentropic. So therefore, the process 3 to 4 now will become isentropic. So instead of having a constant enthalpy process at 0.3 to 4, you can see here this is vertical, meaning that is constant enthalpy. This now will become isentropic. So the same also with the compression, which is isentropic. We are going to make the expansion isentropic. So that is what we meant by an isentropic turbine here at 0.3 to 4. So we already know that the sum of the enthalpy, all we have to do is just to compute now the enthalpy here when we will use an isentropic turbine instead of using expansion valve. But the first step is using isentropic turbine. So we will have to compute now the entropy instead. Since 0.3 is fixed, because that is just the inlet at that point, S3 is the entropy at 0.3, and we have to calculate entropy for us to get the entropy at 0.4, since now we have isentropic process. So the entropy at 0.3 is SF at 297.15. Take note that this one is 297.15, the condensing temperature. So we can get that also from the software, and that is 1.8645 joules per kilogram Kelvin. And since S4 is equals to S3, then we can get S4 as 1.8645 joules per kilogram Kelvin. We are going to use this entropy now to get the enthalpy at 0.4. So the enthalpy at 0.4, instead of having an isentropic process wherein point 3 and point 4 are the same, now they are not the same. So these are no longer this will no longer be 456. So how to get to our enthalpy at point 4 now, or the isentropic enthalpy at point 4 is the enthalpy at pressure 4 and S4. Since we know the pressure at point 4 based on the table that we already tabulated a while ago, then we can compute the enthalpy at point 4. You can also use the temperature. So you can use either of the temperature or the pressure. So here I use pressure. So you can use the system or software. Just plug in pressure and then entropy of 1.8645. Our enthalpy at point 4 will be 440.3 kilojoules per kilogram. Again, before, just look at the table, and then S4 is 1.8645, and using the software, the enthalpy at point 4 is now 440.3. As you can see, it has decreased from 456. When we use isentropic turbine, the enthalpy at point 4 now will become 440.3 kilojoules per kilogram. So the coefficient of performance can now be calculated using these new enthalpy values. So that can be computed as COP is now QL over work net. So that is just QL, or that is now our QL. Instead of using 4, it will become H1 minus H4S, because this no longer is true. We already have 0.1, 0.3, and 0.4S. So this 0.4 now is this is no longer what we are going to use, because again we have isentropic turbine. And then for the work of the compressor, that is just the same, H2 minus H1. So we have this one. And the work of the turbine. So take note that when we use a turbine, our work net will become work of the compressor minus work of the turbine, because again the turbine or the expansion process loses work. That's why we have to subtract it from the work net. So we have H3 minus H4S. So now we can get the COP by substituting all the value that we already have, and that is 5.63. The COP when using isentropic turbine is 5.53. So based on this, the replacement of the expansion valve with isentropic turbine causes the COP to increase by 9%. So that it has increased from 5.07 to 5.53. So therefore, we can recommend the replacement of expansion valve with the isentropic turbine for the process 3 to 4. So having said that, we already have all of the unknown for that